Hi, this is our work on what matters in unsupervised optical flow. My name is Rico, and this is joint work with Austin, John, Ariel, Kurt, and Anelia. The problem of estimating dense optical flow, or dense pixel correspondence, is given two images, image 1 and image 2. You want to estimate for each pixel in image 1 where that pixel goes in image 2. And we represent that with a vector of the relative pixel coordinate. But we estimate that vector for every pixel in the image, giving us a dense flow field. But why is this problem difficult? Shouldn't it be as easy as just matching two pixels that have similar RGB values? It turns out it's not that simple. If we look at these two images, for example, we see large amounts of shadows, reflections, and deformations. That means that pixels can have different RGB values, even though they represent the same thing. And then we have regions with low texture and repeating patterns, such as the road or the facade on the left side, with patterns such as doors and windows that repeat in fixed intervals, making it hard to locally estimate if something moves forward or backward. And then we have pixels that are simply occluded in the other image and therefore not visible, or that leave the image boundary altogether. These effects combined mean that the flow is underspecified, and we need heuristics to fill in the blanks. There are different approaches to optical flow estimation. There are traditional approaches that perform optimization during inference. Those approaches typically try to match pixels that have similar RGB values and estimate a smooth flow field. Then there are supervised approaches, which learn usually from synthetic labels. And then there are unsupervised approaches, which are a hybrid of the two. They learn models similar to those used in supervised methods, but they train them not with labels, but optimizing objectives that are similar to those used in traditional methods. A number of techniques have been proposed here. The performance has steadily improved, but going forward there's a problem because each method uses a different set of core components, and we don't really know which ones are required to achieve good performance. That's why we conducted a study into what matters in unsupervised optical flow, and we performed a large number of ablation studies and comparisons. I won't be able to go into detail on all of them, but I want to share a few results with you. First, on the core components of unsupervised optical flow, that is occlusion masking, smoothness, and self-supervision, we performed an ablation where we tested all combinations of switching those on and off. And we found that all of them are essential to achieve optimal performance, as we can see in this table. We can also see this qualitatively by looking at scenes from KITTI and from Sintel, and comparing their ground truth optical flow to the optical flow estimated by our different methods. So in the first column, we basically applied the full model with all the core components. And as we move more to the right, we then remove different components one at a time and see how the quality of the estimated optical flow degrades as we do so. And then we also look in much more detail to different components. For example, into the photometric loss, where here we compare the L1 loss, the Carbonier loss, the SSIM loss, and the census loss. And we do so in two different settings, in the minimal setting and a full setting. The minimal setting is basically the setting where we switch off all the core components, which I just showed you. The full setting is where we use all of them. And we find that we actually get very different results when we do so. For example, the L1 loss performs worse than the Carbonier loss in the minimal setting, where the Carbonier loss outperforms it in Sintel and KITTI. And this is what you would expect, as most people use this loss rather than this. But if you go to the full setting, we see that L1 actually works better than Carbonier loss, which is quite surprising. But both of these don't work as well as the more complicated SSIM and census loss, which look at image patches rather than single pixels. But again, we see for Sintel, for example, that the SSIM loss works better in the minimal setting, but in the full setting, census actually outperforms SSIM. On KITTI, census works better in either case. Another component we're looking at is smoothness. For example, which level to apply the smoothness loss on. To give a bit more context, we normally estimate optical flow not up to the full resolution of the image, but 2 levels below that, so that's at a quarter of the resolution. And then we upsample flow to the original resolution at level 0, so 0 just corresponds to the full resolution, which is where we apply the photometric loss. And normally that's also the level at which we apply the smoothness loss. But we found that there's a problem when you apply smoothness to an upsampled flow field, because this is going to be piecewise linear, which doesn't work well with second order smoothness. So we proposed applying the smoothness loss at the resolution at which the flow was estimated to address this issue. And we see that it consistently improves performance relative to estimating it at level 0. And then the second table we can see here is looking at the different edge weights that can be used for edge-aware smoothness, where we basically weight smoothness by RGB edges. Here, lambda is what is controlling the edge weight, so 0 means there's no edge weight, we're basically just applying normal smoothness. 150 means we have a quite strong weight on the edges and only enforce smoothness where there are no image edges. And we generally see that edge awareness is very important as it achieves lower results, especially in the full setting. But there was something surprising here that I wanted to share with you, which is in the minimal setting, so this is not using any occlusion estimation and not using any self-supervision, and without edge awareness, so the weight is 0, we get 4.15 endpoint error, which is actually beating state-of-the-art at that point. So this is only using second-order smoothness without edge awareness and a census loss. That's the simplest thing you could think of, and it's beating state-of-the-art on the KITTI dataset. One reason why our method performs so well, especially on KITTI, is another thing we found out about that dataset, which is that it's quite sensitive to which resolution you apply the model at. Just to be clear, this is not the resolution at which we evaluate the method, it's just the resolution at which the model operates, and then the output is rescaled to the original resolution so that the evaluation is fair between those cases. And here we see that if we apply the model at a 640 by 640 resolution compared to the original one, so note that the aspect ratio is very different here, we actually improve performance by about 25% just by changing the resolution. This is something we only found for the KITTI dataset, and we have some hypothesis on why this could be the case in the paper. Now, if we combine all of our findings, we get a very simple method that achieves state-of-the-art in unsupervised optical flow and produces high-quality flow estimates, as we can see here. It also estimates occlusions very well, so that the predicted occlusions match the ground truth occlusions. Comparing quantitatively, we see for both sinter, clean, and final that our model performs substantially better than previous methods, going from over 6 to 5.2 and from about 7.4 to 6.5. The numbers in brackets here are not comparable because they mix training and test data. And especially for KITTI, we see substantial improvements, going from over 5.5 endpoint error down to 2.8 and going from 14% down to 11%, which is actually comparable to the performance of FlowNet 2, which is a supervised method that trains on labels in that domain. So that's all I have. Thank you for your attention. Please check out the paper with link to the code. Please build on our method. That's why we performed this study, and that's why we try to open source a simple state-of-the-art method. And if you want to know more, it would be great to see you at the virtual poster session. Thanks.